So welcome back. Today we're going to be learning some really exciting eigen stuff. So before we get into that, let's think about this equation here. When we look at this, our automatic instinct is probably going to be like, okay, so how can we solve for x given a specific b, given an a? But let's think about it in a slightly different light. So if we look at this left side of the equation here, when we multiply our x vector by matrix A, we're going to get out some entirely new vector, unless A, of course, is the identity. So what this tells us is that we are transforming x into something new, or we can think of A as like a cocoon that's wrapping itself around our x vector, and then transforming into a beautiful new butterfly or new b vector. So it can change its magnitude or its direction or both. So let's look at a specific case of this linear transformation as to when maybe we might get this out. So if we take our matrix times some x, and then we get just a multiple of our x vector out, this is a special kind of linear transformation, and this is going to be our eigenvector. You see it shows up on both sides of the equations, and this here is our eigenvalue. This matrix A does not change the direction of x. All it does is change its size. It'll either lengthen it or shorten it or flip it over, but it'll still be going the same direction. It's going to be along the same line. So now let's look what kinds of x vectors we can pull out that are going to have this property. What we can do is we can take and subtract our right-hand side from both sides. So we'll have a times the x vector minus lambda times the x vector is equal to the 0 vector. And then we can factor out our x vector. So we'll have a minus lambda, but we can't subtract a scalar from a matrix, so we're going to multiply I by lambda. So then we'll have this new equation. So basically we're going to be finding the null space of this matrix here. We don't want this x vector to be equal to the 0 vector, because by definition of an eigenvector it cannot be equal to the 0 vector. So if this matrix here has a determinant that's not equal to 0, that means it's invertible, which means that we can multiply both sides by the inverse, and then x will be equal to our 0 vector. So since we're trying to find eigenvectors which can't be 0 vectors, we need this determinant to be equal to 0. So what we're going to do is we're going to find a matrix for some value of lambda that makes our matrix A have a determinant of 0. So what multiple of our identity we can subtract from A to get a matrix with a determinant of 0, and that, my friends, is what we're going to use to find our eigenvalues and eigenvectors. So let's look at this for a very specific example of A. So now we have this specific example of our A. We're having a 2 by 2 matrix of 7, 4, negative 4, negative 3. And we're going to follow these steps here to find our eigenvalues and our eigenvectors. So our first step is to find A minus lambda I. So we're going to take A minus lambda I by taking our A, which is 7, 4, negative 3, and subtracting from it our lambda I. So if we are dealing with a 2 by 2 matrix here, we're going to want our identity matrix to be a 2 by 2. We multiply lambda by every term in our identity, we're going to end up with this matrix, where we have lambda down the diagonals and zeros everywhere else. So then when we take A minus lambda I, we're going to end up with this matrix. 7 minus lambda, 4 minus 0, negative 4 minus 0, and negative 3 minus lambda. So now we have found A minus lambda I. So now let's move on to our second step. We want to take the determinant of this new matrix. So we're going to take the determinant of 7 minus lambda, 4, negative 4, and negative 3 minus lambda. So we go multiply down the diagonal to the right, So we have 7 minus lambda times negative 3 minus lambda minus the diagonal going the other way. So 4 times negative 4. So now this is going to be equal to the determinant of a minus lambda I is equal to 7 times negative 3 is going to be negative 21. 7 times negative lambda is negative 7 lambda. But then we're going to have a plus 3 lambda right here. So we're going to have a negative 4 lambda. We're going to have a plus lambda squared. Then we're going to be subtracting this, which is a negative 16. So then we know that our determinant of a minus lambda I is equal to lambda squared minus 4 lambda. Negative 21 plus 16 is negative 5. Okay, so now we know what our determinant is equal to. And then for our third step, we are going to set this equal to 0. So we're going to have lambda squared minus 4 lambda minus 5, which is our determinant of a minus lambda I. We set that equal to 0. So then when we factor, we will have lambda minus 5 and lambda plus 1. That equals 0. So now for our fourth step, solve for lambda, we're going to see that lambda equals 5 and lambda equals negative 1. We always like to number our eigenvalues. So see, we found our eigenvalues. We like to number them so we can keep track of which eigenvalue we're talking about and which eigenvector corresponds to them. So now we're going to come on up over here and we're going to do our fifth step, which is solve for the null space of a minus lambda I for all lambda I. So we are going to take our first eigenvalue, which is 5, and we're going to solve for the null space of a minus 5i. So we're going to solve this equation here. So this is going to be our eigenvector here, and this is going to just be, just so you know here, this is going to be x1, x2. That's our eigenvector. Okay, so now let's solve for this null space. So we know we're going to have to take a minus 5 lambda, so we're going to take our a, which is 7, 4, negative 3, subtract 5 lambda from that, so we're going to have 5, 0, 0, or 5i, and that's going to give us this matrix. 7 minus 5 is 2, 4 minus 0 is 4, negative 4 minus 0 is 4, and negative 3 minus 5 is negative 8. Now we're going to solve for the null space of this matrix, so we are going to take 2, 4, negative 8, augment it with the 0 matrix, and then reduce it down to see what our x sub 1 and x sub 2 are going to be equal to. Okay, so from here this tells us that x1 plus 2x2 is equal to 0. And then our 0x1 plus 0x2 is equal to 0, so this is the only one we're concerned with. And we have x2 as a free variable. So then we're going to know that x1 is equal to negative 2x2. So we go to solve for our eigenvector. We're going to call it v sub 1, so it has the same subscript as our eigenvalue. That's going to be equal to x sub 1, x sub 2. But we know that x sub 1 is equal to negative 2x sub 2. And then x sub 2 is just equal to x sub 2. So you always write our eigenvectors in terms of our free variable. So we're going to have our eigenvector is going to be equal to x2 times our negative 2, 1. So our eigenvector here is negative 2, 1, but we notice here that we have our free variable x2 hanging out up front, which means that any multiple of this eigenvector is also an eigenvector. So let's just actually check to make sure that this is an eigenvector. We would expect a times v1 to be equal to lambda 1 times v1, correct? Because that's our definition of eigenvector. So now what we do is we take our a we have 7, 4, negative 4, negative 3. We're going to multiply that by our eigenvector here, which is 2, 1, negative 2, 1. And we're going to see what this is equal to. So we have 7 times negative 2, which is negative 14, plus 4 times 1. So we're going to leave us with a negative 10. We're going to have negative 4 times negative 2, which is 8, plus negative 2, or negative 3 times 1, which is negative 3. So we're going to have 8 minus 3, which is 5. So we notice that this is equal to 5 times negative 2, 1. So our eigenvector here, this negative 2, 1, when we multiply it by our A, we're going to end up with 5 times negative 2, 1. And this is our eigenvector here, or eigenvalue here, and eigenvector here. So that means that we have successfully found the correct eigenvector for lambda 1 equals 5. So let's just write that up here. And now let's go through and solve for our other eigenvector. So now we're going to consider our second eigenvalue here. We're going to look at lambda 2 equals negative 1. We're going to be looking for V2. So our second eigenvector. So we are going to have A minus negative 1i, and that's going to be equal to A plus I, which is, we know, 7 plus 1 is 8, 4 plus 0 is 4, negative 4 plus 0 is negative 4, and then negative 3 plus 1 is negative 2. So now we have this, and we're going to try and be solving for the null space of this matrix, so we can augment it with our 0 vector, and we are going to go ahead and solve this. So then this tells us here that x sub 1 plus 1/2 x sub 2 can be equal to 0. So this tells us then that x sub 1 is equal to negative 1/2 x sub 2. So once again, we're going to take our eigenvector here, b sub 2, set it equal to our x sub 1, x sub 2. And that's going to be equal to x sub 1 is equal to negative 1/2 x sub 2. And x sub 2 is just equal to x sub 2. Because once again, x sub 2 is our free variable. So we're going to end up with this. We're going to have x sub 2 times negative 1/2, 1. So this here, our eigenvector for our second eigenvalue of negative 1, we're going to have negative 1/2, 1. So if you recall, I said that any multiple of our eigenvectors is also an eigenvector. So let's try that out. This is a perfect opportunity because we don't want to try and multiply all these fractions. So let's try it out. We're going to try it like right over here. So if we take our A and we multiply it by 2 times our eigenvector here, so we're going to multiply it by negative 1, 2. We're going to expect to get out negative 1 times this eigenvector here. We have 7 times negative 1 plus 8 is going to be 1. Negative 7, or negative 4 times negative 1 is going to be 4, plus negative 3 times negative 3 times 2 is going to be 6, so we're going to be left with a negative 2. So wait, this is equal to negative 1 times negative 1, 2. So we see here our eigenvector, and we have over here our eigenvector again. And then we see right here, oh look, it's our eigenvalue. So you can see that even a multiple of the eigenvector that we found here is still an eigenvector. So now we have successfully found all of the eigenvalues and eigenvectors of this matrix here, A. So next time we're going to learn about how we can characterize these and put them together. So see you next time.